Scalable multi-robot informative path planning for target mapping via deep reinforcement learning. Autonomous robots are applicable in several tasks such as search and rescue missions, environment mapping, and agriculture. In this work, we develop a decentralized, deep reinforcement learning-based approach for the MRIPP problem. We aim to maximize the number of discovered targets of interest in a 3D environment containing unknown obstacles. As robots and targets to be discovered, we utilize unmanned aerial vehicles and RUCO tags. The challenges considered in this work include the ability of our approach to scale to a greater number of robots deployed in more complex environments without requiring significant overhead. Each robot considering the regions explored by other robots while planning their own paths. As the robots explore the environment while operating under communication constraints, avoiding inter-robot collisions is challenging. Each robot needs to avoid collisions from the newly discovered static obstacles. In our approach, each robot maintains an occupancy map, a Gaussian process to model the target distribution, and a Gaussian process to model the regions explored by other robots. At each time step, our approach samples collision-free candidate actions in the robot's local region. We associate each candidate action with the target distribution features and the exploration features to generate our coordination graph. Our policy network relies on these features to output the robot's state value and the next action to execute, leading to the generation of reward and observations from the environment. The observations are utilized to update the robot's internal representation of the environment for future planning. During training, we store the coordination graph, state value, executed action, and reward in an experience buffer for on-policy training of our actor-critic neural network. Our new reward structure considers the exploration-exploitation trade-off, as well as encourages inter-robot communication within the multi-robot system. Our reward structure consists of exploratory reward, utility reward, and communication reward. We now present the comparison of our approach with other state-of-the-art learning and non-learning approaches. Our results indicate that our method outperforms the considered baselines in terms of the number of discovered targets. Note that introduction of communication constraint leads to a drop in the performance of our approach. However, we still outperform the considered baselines operating with global communications. We next present the performance of our approach when deployed in more complex environments with larger number of robots in the multi-robot system. We compare our approach operating under communication constraints with a learning-based approach operating with global observability and a random planner. Our approach strongly outperforms the considered baselines in 3x larger environment, slightly outperforms in 8x larger environment, and is outperformed in the 16x larger environment. In the 16x larger environment, the communication among robots located further away drastically reduces, causing our approach to be outperformed by the planner with global observability. We present the performance of our approach implemented in a simulator for the task of urban monitoring. Our environment consists of 9 differently sized buildings placed in a 3x3 array. We consider the windows on the buildings as the targets to be mapped. As shown in the videos, we deploy 3, 5, 7, and 9 UAVs with a budget of 2.66 units per UAV. We trace the paths followed by each UAV using colored trace lines. Finally, we deploy our approach on real robots using RISE Teo drones. In this experiment involving 2 UAVs, we demonstrate the applicability of our approach on real robots. Here, we use RISE Teo drones as our UAVs and RUCO tags as our targets to be discovered. Our approach is able to avoid collisions with unknown obstacles in the environment. In this experiment involving 4 UAVs, we demonstrate the scalability of our approach to larger number of robots without requiring additional overhead and deployment. Our approach is able to plan paths for each robot in a decentralized manner. Our approach not only avoids collisions with unknown obstacles in the environment, but is also able to prevent inter-robot collisions throughout the mission. Thank you.